Hello, everyone. If you're in back, I can look in the middle here, and I do see some seats. And I will not be offended if you sort of come down and sort of, scrooch in. Feel free. So it's really my pleasure to be here and tell you about some of the work that's going on in my lab. I'm part of the physics department. I'm part of JILA. I'm part of NIST. And we love all of it. And we have a good time. So let me jump right in and start with sort of a very broad, maybe you're a first-year grad student. You don't know about all this atomic physics stuff that we do. Let me just motivate, why is it that we like to work with atoms, okay? And why is it that, you'll see a lot in the Boulder area of use of, for instance, atoms or molecules for making very precise measurements of the universe around us? Well, people have been building clocks for a long time. So for instance, here's a water clock, and basically, water flows by, turns a wheel, and somehow that sort of, keeps track of time for you. But of course, if you built another one, it may not tick at the same rate, or maybe the ticking rate actually depends on, how much rain you had, something like this. And so in fact, they're not very accurate. They're not very reproducible. What we really take advantage of with atoms and molecules is something we don't talk about very much, but it's not the quantum uncertainty principle, it's the quantum certainty principle. Quantum mechanics tells us, as best we can tell, that all atoms are identical to each other, okay? And this is very, very important. We leverage that fact. So how do we leverage that? Well, okay, so you write down the Schrodinger equation to describe some orbiting, let's say, electron around some nucleus over here. And when you solve that Schrodinger equation, you end up with discrete orbits with discrete energies over here, okay? It's one of the first things we learned about quantum mechanics. It gives us this. And the point is, if I grab a rubidium atom and I look at sort of, what orbits are allowed on my side of the universe, and I do the same thing, on the other side of the universe here, and if they're both rubidium atoms, say, I'll see the same spectrum. They're identical to each other. And we're really going to leverage that in order to do interesting physics. I'm not going to get into the details of exactly how you do this, so here's kind of like the very high level of how do you leverage that accuracy, okay? Imagine that you use atoms as clocks, and we'll talk about that a little bit later, how you do that. But imagine, for instance, you had a strontium clock based on strontium atoms, and you had a clock based on, say, ytterbium atoms. In fact, those exist right here in the Boulder area, okay? And imagine that there's some stuff. What is that stuff? Who knows? It's dark matter. It's something that we have yet to discover. It's some new particle, some new field. But it turns out that depending on the details of the atom, the stuff may tickle the properties of these atoms in different ways when it interacts with it. And by looking at sort of differences in how, for instance, these two different clocks that you might build with two different atoms, how they actually change as a function of time, because we believe things are identical, if there's some relative change in the ticking rate, it tells you must be interacting with something you're not seeing. And that's really the spirit of a lot of these quantum sensors for precision measurement in fundamental physics. There have also been proposals, for instance, where you say, I put two identical clock-like objects, say two strontium clocks, separated maybe in space, separated by thousands of kilometers from each other. And you send light pulses back and forth to sort of communicate the ticking rates of these two clocks. And if a gravitational wave comes by, you would actually observe sort of the stretching of space-time as the gravitational wave goes by, okay? And so there are proposals originally for doing this with things that you may be less familiar with, but I'll talk about during this talk, called matterwave interferometers. But then that was extended to the idea of using clocks. And in my group, we said, well, what are the atoms really doing for you in these? And we really kind of mapped it onto the atoms are kind of acting as a quantum memory of the phase of the optical light pulses that are being exchanged. But these are some examples of how you can really leverage these atoms to do interesting fundamental physics. There's also, honest to God, applications for these things, okay? Not just fundamental physics. We have this thing called the SI system. And in fact, with the association with NIST, we really care about this stuff, okay? And it turns out that when you make measurements, you just take it for granted that we know what a second is and we know what a meter is. But in fact, we use the quantum certainty principle to define, for instance, the second in terms of, say, the transition frequency of some transition within cesium, and eventually you'll move to some optical transition. okay, the definition. And then you use that to actually realize all these other units over here. You can define the meter, kilogram, et cetera. You leverage that definition. In addition, we've all gotten spoiled. We turn on our phone when we don't know where we're going. We got to find a new restaurant. We use GPS, the global positioning system. It's just a cloud of clocks in space. Whenever I say that, I always think pigs in space. Those who are a little bit older may know what I'm talking about. But anyways, we've got all these clocks floating around in space, okay? And essentially, you're sitting here on Earth, you're listening to the ticking of these clocks, and it tells you, oh, turn right. Take a right-hand turn right now, okay? Cool. So when you think about building, for instance, a modern optical clock, it turns out it's actually limited often by the laser frequency noise. It's actually not the atoms. They're the limitation on how good of a clock you can build. So, when you and I think clock, oh, hey, look, there's one right there. You look there and you say, well, like I've got these hands and they continuously go around, right? They tick as they go around in some continuous way. In reality, in an atomic clock, the thing that is the clock is actually the laser, right? The electric field goes up and down as it goes by you. That's the ticking, okay? We use the atoms in this quantum certainty principle to say, well, actually, is it ticking? Is the frequency of that light at the right frequency? To do that, we actually probe some atomic transitions over here and check to see if that laser light is resonant with an atomic transition, and then we steer the frequency to match that atomic transition frequency, okay? So the atoms are really just a frequency reference. They guide the ticking rate of the laser. So if I have a lot of frequency noise or phase noise on this laser, it actually means that sort of my little ticking clock over here actually has a lot of jitter in it, okay? It's not a great thing. So I'm going to tell you 3 stories today. And so story number 1 is about how we are trying to break through thermal limitations on laser frequency noise with the goal of achieving 100 times reduction in laser line width for frequency, length, and gravity metrology. Okay, that's sort of the broad topic. Let's come back to this quantum mechanics sort of quantum certainty principle. When I was writing this, I think I was feeling very biblical. Quantum mechanics giveth and taketh over here. And so we have this quantum certainty I've told you about. But in fact, what we're used to hearing about in quantum mechanics are things like quantum uncertainty principles, right? The Heisenberg uncertainty principle. And in fact, that's true in quantum sensors. There's some kind of intrinsic quantum fuzziness that we'll talk about when I, for instance, have a collection of n spins, and there's some fuzziness in the orientation of that spin, and it's the orientation of that spin that we use to build our quantum sensor. And so this is really a fundamental limit for all quantum sensors that we build, this quantum fuzziness. So that brings us to story number 2, which is how we can squeeze the quantum uncertainty in our system. And the goal here is to really create a sharper pointer for measuring the universe around us. And in particular, I'm going to tell you about some stories in the context of matterwave interferometers and clocks and applying there. Yes?
On the previous slide.
Mm-hmm.
So you talked about the laser, and maybe one with that.
This one?
Laser versus the atom. So,
Yeah.
atom has some, atomic transition has some width.
Mm-hmm.
The laser has some jitter.
Yep.
So which one is limiting?
It's the jitter of the laser.
The jitter of the laser.
Uh-huh.
But presumably then the atom then you can use as a feedback.
Exactly, and that's what you do. So you say, oh, look, I'm not quite on resonance. My laser's not quite on resonance, so I'll feed back on the frequency of the laser. That's exactly it. Mm-hmm.
Okay, so the clock, atom.
An atom is a frequency reference. The thing that's really ticking in a continuous way, what you and I would think of colloquially as a clock, it really is sort of the laser. That's the thing you deliver that has a continuous phase. Yeah. Sorry, I really, I'm a stickler for the English language. Like when we say clock, we mean something that really continuously ticks. Okay. The atom definitely doesn't continuously tick. Okay. At least in this version of a clock. I'll show you a different one. Okay. Okay, let's keep going. I keep having little meltdowns with my clicker here. I'm going to have to stay closer. Great. So the idea is, can we create entanglement between the atoms in such a way that we can reduce the sort of fundamental quantum fuzziness? I'll tell you some stories associated with that. And then finally, this quantum certainty, coming back to the quantum certainty, what it does for you is it turns out we can develop techniques like optical pumping and coherent couplings that allow us to create states with very low initial entropy. We can create states where atoms interact with very tunable interactions, and we can also apply tunable disorder in our systems. And so this is going to be really, really interesting for thinking about quantum simulation. So story number 3, if I have time, is going to be talking about some work we've done recently on emulating some dynamical phases of BCS superconductors using tunable interactions and disorder and the access to unique observables in that system. How can we do all this? Well, it turns out that the atomic physics community has a very long history of working to get control of quantum objects. And so this is sort of represented by this sort of lineage of sort of Nobel Prizes that really represent work of the whole field. Many people contribute to this. There are people up here who you might recognize. I'll wiggle them if it works. Great. These are local Boulder people, and this is another sort of NIST Gaithersburg person that we're happy to also claim, Bill Phillips over here. But basically, there's just been this really long history of getting more and more control of single atoms, single ions, doing whatever you want with them, okay? So what I'm telling you, and I'm not gonna explain in this talk, is that we have nearly complete control of single atoms. I'm not gonna explain to you how we do it, but we can apply lasers that, for instance, instead of making the atoms hot, actually make them extremely cold. We can make the atoms sort of microkelvin temperature, okay, above absolute zero. We can trap them and hold them and suspend them in tractor beams of light called optical dipole traps or optical lattices or tweezers. And we can hold them and we can keep them away from the rest of the universe so they really stay in a quantum regime. They're not interacting with the rest of the universe. We can really suspend them in say, an ultra-high vacuum chamber. We can couple internal degrees of freedom. We can put them in superpositions of states. We can do all these things. What's the next thing we can do? Okay. So this comes to my group. What we're interested in doing is actually seeing how we can generate correlations and entanglement between the atoms, so somehow like connect them to each other. So they're not just independent atoms. And that's going to be facilitated by an optical cavity. An optical cavity here is just a fancy word, if you've never encountered it before, of two shiny mirrors. They face each other, light bounces back and forth many, many times, okay, between those. In our case, about 100,000 times before the photons escape. That's the scale. And that light going back and forth is going to mediate interactions or provide information to us that's going to be useful. And the themes are we're going to explore fundamental science of quantum sensing, metrology, and many-body physics. And one thing that's a little bit unique in our lab is that we use all of quantum mechanics. We use unitary dynamics, dissipation. Many people do that. We actually focus a lot on the quantum measurement process, and I'll try and explain that a little bit along the way. Okay. There are 4 experimental platforms currently in my lab, which are these optical cavities, sometimes called cavity QED. These are not typically, for 3 of them, these are not single atom experiments. We typically have around 1,000 to 1 million atoms inside of our optical cavities. I'm going to tell you some stories today that focus on these 3 experiments. Unfortunately, I don't have time to tell you about this 4th one, which is a beam of thermal rubidium atoms going between 2 very tightly or small space mirrors, okay? And with that, we're going to generate non-classical light for the masses. This is going to be everybody's non-classical light source. That's the goal, to make it sort of very compact and easy to distribute. And so there are 2 people, actually 3 people, right here in this audience, I'm guessing, who you can find, and you can ask about this. And there's a paper if you wanted to read it over here, but this is in collaboration with John Kitching's group down the road as well. Okay? So I encourage you to do that. So let's talk about story number 1. Story number 1 is breaking through thermal limits on laser frequency noise. And again, the goal is to make a very, very narrow line with lasers. So let me tell you that story. So how do we make good lasers anyways these days? Well, the best way we know how to do it is you actually take two mirrors, just like we talked about, to form an optical cavity. And the separation between the mirrors defines a resonance condition, okay? Just like the length of the string on a guitar defines the note, okay? And so by holding the separation distance, between these two mirrors very fixed and very stable, you have a very stable resonance frequency. And now what you do is you take your laser, whose frequency you want to stabilize, and you steer it to match the resonance frequency of this cavity over here. Okay, that's the best we know how to do. Works really well. People who are here in JILA, like Jun Yi, down the road at NIST, man, they're really good at this. Okay, but is this a hard problem or not? So let's say you have a buddy, and you're sort of talking one day, and they say, hey, look, could you make me a laser that has a fractional frequency uncertainty, this delta F over F of 10 to the minus 17? You go, sure, no problem. So you start thinking about it, and you say, okay, well, I'm going to space those mirrors apart by about, I don't know, 1 meter. That seems like a good length. So you space them apart by 1 meter. And you calculate, and you go, oh, gosh, I'm going to have to hold the mirror separation fixed to about 10 to the minus 17 meters. Let me remind you, the size of a single nucleus is around 10 to the minus 14 meters. It's non-trivial to do. So all kinds of things can mess this up. People can stomp around the lab. People can talk too loudly. People can open Coke cans. Things can happen, okay? And it causes vibration. And so they've worked very hard to build vibration isolation systems. They get rid of all of this source of vibration noise, and yet it still looks like the cavity length is jittering. And it turns out the reason for that is there's actually thermal motion. This thing is made of real atoms. They have kBt of energy, right? They're jiggling around. And as a result, this sort of thermal motion of the spacer, the reflection coating, and the mirror substrates, all of that matters. It's changing the cavity length, okay? This has been a really hard problem. Amazing progress has happened, but I can't even begin to tell you how many sort of years and years and years of research effort has gone into getting rid of this and making it better. Great. So there was this idea that was put forward in 2009 by Meiser, Yi, Carlson, and Holland. Yeah, maybe you recognize those names. Those are the home crowd right here. They said, look, what if we build a laser using nature's high Q optical oscillators rather than a length artifact, where you have atomic transitions of line widths around 1 millihertz to a hertz? What if we could just get light directly? Okay, that was a proposal, as well simultaneously Chen here in 2009. I want to take a moment and credit that this is per June in having conversations with him, that in part this project was inspired by a conversation between June and Dan Kleppner. Some of you know who Dan Kleppner is, some of you don't. Dan Kleppner, for me, is an academic grandfather. He was my advisor's advisor. Eric's as well. I don't know if anyone else is in the room. I just want to say, if you're in the field of atomic physics, it's a relatively friendly field. We kind of get along. It's a good field to be in. We're pretty happy. And I just want to say that I think Dan Kleppner is one of those people who helped to make it that way. And I think that has to be a choice in a field, to actually say, we're going to make this a nice field to work in. Okay. Anyways, I think he deserves a lot of credit for that. It's very sad that he passed away about 2 months ago. Okay. Great, but it turns out Dan Kleppner was the inventor of the hydrogen maser. And he said, hey, June, you're working on all these lasers. What if you just build something that looks like a maser, but in the optical regime? Okay. And that sort of spurred this proposal. So we thought that was really interesting in our lab. And we said, well, we're not going to build the real laser we want in the long run, but let's build sort of a fictitious one that has all the same physical properties that we'd want in the long run. And when we did that, we were able to show that we could get a laser that we built here that achieved lasing with less than 1 photon inside the cavity. It's a nearly lightless laser. There's very little light coming out of it, okay? Man, you can look right down the bore of this thing. You're not going to blind yourself. You don't need goggles, okay? But what's interesting about this is, for me, it's a conceptual question of, well, look, if the average number of photons, we went as low as 0.2 photons on average inside the cavity, if you think about that, just like for position and momentum, there's a number phase uncertainty principle that you can write down. And if your average number of photons is so low, in some sense, your phase uncertainty is very high. The phase of that light. What do I mean by phase of light? Should I be a cosine right now or a sine, omega t, right? That's phase. And when I think about that, it's like, well, look, normally in a laser, I think of the light as keeping track of the phase of the laser. But it's pretty ill-defined here. Who's keeping track of it? And so, in fact, it's the atoms. We're using the extreme coherence of the atoms to sort of act as a phase memory in our system. And so to contrast, here is the limit of a standard optical laser, where we think of it as we have atoms and we have the cavity. And these are little photons streaming out. They come out of the cavity at a rate kappa. That sets a line width for the cavity, which is this little narrow thing here. And then you have a gain medium. And in our case, it's real atoms. It's not a hunk of material. It's just atoms in a vacuum chamber. And that acts as the gain medium, and it also has some frequency line width. And it's much broader, that sort of gain line width. And in that case, what normally keeps track of the phase is the photons. So the photons are the flywheel or the phase memory, and the oscillation frequency of the laser follows the cavity resonance frequency. We're working in the opposite limit, where in fact, the atoms are very narrow in their atomic transition, and the cavity is very broad in comparison. In this limit, the atoms are going to act as the flywheel of the phase memory, and the oscillation frequency follows the atomic transition frequency. Okay. So we did this synthetic experiment. We thought this looks really good. Let's go and find a real narrow transition. What do you know? A favorite atom around here is called strontium, and so we went to strontium. So we built a cavity QED system where we packed about 1 million strontium atoms inside of here. It has a triplet to singlet transition, J equals 0 to J equals 0. Highly forbidden, but it still decays. Decays with a sort of a time constant of around 120 seconds. Man, this is a transition that does not like to emit light. We're foolhardy enough to say we're going to make it emit light. Okay, that's what we're going to do. Okay, so this thing lives forever. We pack all these atoms in, and we actually prepare at t equals 0 all the atoms in the excited state. We wait, and nothing happens. Nothing happens. We're looking at the output power from the cavity. And then suddenly the output power goes up and comes back down. This is non-exponential. This is not single particle decay. In fact, this is reminiscent of something called Dicke superradiance, is what this is reminiscent of. Okay? And so that's what we're thinking. We're generating these sort of superradiant pulses of light in which the symmetry or the collective dipole moment of the atoms themselves stimulate more emission of light out of the cavity. Okay, and so that's described in these papers. We can do it at different atom numbers over here. But we can also ask, by taking advantage of ultra-stable laser light from Juni's lab, we can actually ask, for each pulse of light, how stable is the frequency of that pulse of light? Okay? And when we do that, we see that one pulse of light has a fractional frequency uncertainty of 7 times 10 to the minus 16, one pulse. We create one pulse per second. We create a pulse of light, we throw the atoms away, we load more atoms, we get another pulse of light. Okay? And so this seems pretty encouraging. It's already the most precise active atomic clock that you can build, because this frequency is tied to the atomic transition frequency. What's super exciting is you can change the cavity resonance frequency and see how much the frequency of the light changes by. And the answer is we're 500,000 times less sensitive to cavity frequency changes. Mm-hmm.
It's a little confusing. I mean, you said the phase is very extremely uncertain.
Yes.
But then
You're putting atoms, many atoms, these N atoms, in a superposition such that all the atoms are in some sense pointing the same way. And it's that sort of collective block vector that's going to hold the phase information in the system.
if I think of
Mm-hmm.
the optical signal,
Awesome,
the
great.
phase,
Perfect.
quantum fluctuating phase, then it doesn't.
Perfect. So, exactly. So what I told you was the atoms are interacting with a photon field inside the cavity, which is given by an average photon number of 0.2. But when I make my measurement, I can collect all the photons that come out. And when every atom decays, I get about 1 million photons. Does that make sense? It's a great question. Mm-hmm. So there's this weird thing in quantum optics where you have to define the mode, and you can even define it after the fact in the data analysis, about which you want to make a statement. Okay? And in this case, I would define a mode which is defined by this sort of pulse envelope. Okay.
James, what makes these pulses so nearly symmetric in time?
Okay, here's the quick view of it. I have a, yes, I'm going to do it now. I have other slides that might help with this, but let me do it anyways. I put all the atoms up. I describe this with a collective block vector. If you don't understand, we'll talk about it later. A collective block vector pointing up. Some quantum fluctuation kicks it over just a little bit. Spontaneous emission into the cavity. And then what happens is I create a collective dipole that is proportional to the projection of the block vector onto the equatorial plane. That's the thing that radiates. And so what happens is it goes over, I create a radiating dipole, which causes it to tip faster, and then it hits the equator. And when you're at the equator, that's when you hit your peak over here. And then when you go past the equator, the projection onto the equatorial plane goes down. Okay. Yep.
Did you actually need a cavity, or what happened?
What I don't understand is if I don't have a cavity, what we really want to see here is something called line width narrowing. If I don't have a cavity, I think that breaks down. So in this case, I think the cavity is important for the line width narrowing.
Question.
Mm-hmm.
Is the moment it turns on stochastic?
Yes. It's there.
That's a single pulse.
That's a single pulse you're seeing. It's a single shot pulse detected on SPCM with some sort of time averaging to sort of average over all the little fluctuating photon counts. Mm-hmm. Yep. Okay. If a pulse is nice, wouldn't it be great to go to CW? Let's not get pulses of light. Let's just have like a normal laser, like this laser pointer, just continuously giving us photons. Great. If you could do that, it turns out that we think we could start reaching of order 10 to the minus 18 fractional frequency uncertainty at 1 second of measurement. How precise is that? If I were to move my clock up by about the width of my thumb, the flow of time changes by about a part in 10 to the 18, okay? So you could measure a change in your height and the gravitational potential in about 1 second at the centimeter scale. This would actually be super useful, for instance, high bandwidth geodesy, gravitational wave detection, and dark matter searches are some possible applications. And so here's the apparatus that we built to do that, and there's some glowing strontium atoms sitting here in a ring cavity that we're building to do that. It's a ring cavity because, make sure everything appears there. There we go. We're going to continuously load atoms from up here, trap them, and then have a conveyor belt to transfer them down here, where there's low decoherence on the atoms. The atoms become very narrow again because we're not cooling them, and then we can get lasing. Okay? And so here's just some pictures of us doing transport inside the cavity, and I'll encourage you to look at these references over here. Okay. Mm-hmm.
Can you compare this to what you were saying before, where you have your clock as your laser, conventional laser, and then you feed back?
This breaks that. So if we can really build a CW system, it's just one unit. We don't have to have a separate laser. It's just the light that comes out becomes your clock signal.
In terms of precision,
In terms of what precision you can do at short times, it's close. In terms of what you can do if you really go to very long evolution times and you have built like a cryogenic silicon reference cavity and you do all that. It's a different way of doing it. It also says that I don't have to worry so much about vibration isolation because I've got this factor of 500,000. You don't get factors of 500,000 in precision measurement very often. That's why it's kind of exciting. Okay, story number 2. Let me tell you a little bit about that. The goal here is squeezing quantum uncertainty out of the way so we can make sharper pointers for measuring the universe around us. So let's jump right in. So I use some language that for experts in the room you might understand, but the basic model of when I build a precision measurement is I have a lot of levels inside my atom or molecule, but I'm going to say really only 2 are going to matter. I'm going to frequency selective sort of just pick out 2, and I'm going to do all my physics within these 2 levels over here. And the idea is that in some way these levels have some energy difference. And so if I build a superposition between these 2 states over here, there will be a phase difference that accrues at a rate that's proportional to E over h bar. This is just basic quantum mechanics, right? Energy eigenstates. Okay. Your signal, it could be a magnetic field, it could be the flow of time, it could be an acceleration, it could be a rotation. Whatever it is, effectively gets encoded in this phase. And your goal is to estimate this continuous variable phi from some measurement. Okay? you might say, well, okay, this is kind of like a toy model, surely can't explain much. No, we can use it to model matter wave interferometers, EDM experiments, magnetometers, microwave and optical clocks, nuclear clocks, optical interferometers, polarization interferometers, light dark matter searches, blah, blah, blah. We can basically map it onto this model. That's why it's so powerful. Okay, great. Well, we like to use something called the block sphere for describing superpositions of spin halves, or maybe even more than one spin half, maybe like n of them eventually. And so you can think we can parameterize an arbitrary superposition of spin up and spin down here via some polar angle and some azimuthal angle, and we can visualize this quantum state as a point, that's being pointed to by this vector on this sphere, okay, called the block sphere, okay. And so again, it's kind of like, well, if I change phi, I'm just changing the azimuthal angle on this block sphere representation. If I'm all in up, it means the block vector points to the North Pole. If I'm all in down, it's pointing to the South Pole. In the equal superposition, I'm right on the equator. Okay? So theta and phi really are like the normal, spherical coordinates that we're used to thinking about. Great. So I have shown you this arrow. See, it's very precise. See how sharp that little arrow is? It's pointing to a very specific spot. But when we go to actually make measurements of the orientation of that arrow, usually we don't use one atom. We tend to use n of them and run n copies of the experiment in parallel. They're each spin halves. So let's add them up to make a total spin of length j equals n over 2. Okay, just think there's one big collective block vector over here. So there are commutation relationships between angular momentum over here. And you can say, well, let's say my block vector on average is pointed towards the North Pole. I'm up. And if you do that, then you can replace jz by n over 2, because basically you're pointing up. And now this kind of looks like commutation relationships between, say, x and p. And we know that we get an uncertainty principle from those commutation relationships. And it gives you sort of an uncertainty relationship between the spin noise along x and the spin noise along y when you go to make a measurement. If I think of these spin projections as what I'm going to use to estimate that angle, I can say, well, I've got some fluctuation in my spin. What's the arm, which is j? And I just divide by each of those sort of spin projections by n over 2. And I say, well, if I equally distribute the uncertainty between the polar angle and the azimuthal angle, I get 1 over root n radians. This is called the standard quantum limit. We can fix up our previous picture like so, where we draw our block vector. So you're going to see these diagrams a lot in what follows, where we put little quantum fuzzy patches. This is the angular uncertainty that arises from this sort of Heisenberg-like uncertainty over here. That's our visualization of it. Okay? So when we go to make a measurement of the spin projection of this block vector along some coordinate, the degree of fuzziness along that direction will tell us about the fluctuations in our measurement outcome. Okay. Great. So if I start with unentangled atoms, the best I can do is the sort of angular uncertainty gets uniformly distributed. It's 1 over root n radians. And I encourage you to put radians on it. It's an angle. On the other hand, if I actually create spin squeeze states or things where the atoms conspire to work together to partially cancel each other's quantum noise, okay, they're no longer independent, then we can actually reduce the noise along one dimension we care about at the expense of increased noise along the other direction. And we still satisfied the uncertainty principle by doing this. Okay. How well can we do it? Here's my summaries of that. It's not 100% up to date, but it's not so far off. Versus time. So 1 means that you have no improvement due to entanglement at all. It's on a log scale on the vertical, and this is improvement in variance. So sort of like radian squared, like improvement in radian squared. So in fact, some of the very pioneering work was done right here in Boulder in ion traps. And you can look at the different symbols corresponding to using ion traps or cold collisions and things like BECs or Rydberg interactions. And just for reference, I also added squeezed light fields up here, Roman Schnabel's results. People using cavities are the dark points over here, the kinds of systems I'm talking about. And so they can develop sort of unitary squeezing called one-axis twisting we'll talk about, as well as quantum non-demolition measurements. My group are the red points over here, okay? So at this point, it's basically our group and Mark Kasovich's group that can see about 18 to 19 dB of enhancement beyond the standard quantum limit directly observed in these two papers, and actually using somewhat similar techniques, to be honest. And it's a quantum measurement technique that I'll explain in a second. When I've explained the basic idea of these Q and D, I'll then tell you about how we've applied it to a matter wave interferometer and also to differential measurements of atomic clocks. Here's the basic way it goes. The basic way it goes is that we have ground hyperfine states of rubidium here, and we can put atoms in a superposition of these two ground states. We tune a cavity resonance to be close to, but not quite on resonance with the up to E transition. So here's our frequency diagram. Here's the cavity mode. Here's the cavity resonance. Here's the up to E transition. And it turns out that when you put light inside the cavity, as light goes whizzing through those atoms, if the atoms are in up, they create a phase shift on the light, like a piece of glass. And that also actually changes the effective optical path length between the mirrors, and it shifts the cavity resonance frequency. See, it shifted, okay? And it shifts by an amount that depends on the number of atoms in spin up. You can write down a Hamiltonian for this. Sometimes this is called a Q and D Hamiltonian, in which you basically say that the C dagger C, the resonance frequency of the cavity, now depends on the number of atoms in spin up, okay? So if we want to measure the number of atoms in spin up, all we have to do is we have to measure this cavity frequency shift very precisely. And that will actually allow us to determine the spin projection JZ. Because if we know the number of atoms in up, we also then will know the number of atoms in down. That's the spin projection JZ. It's up minus down divided by 2. Okay? Because that's what spin projection is. It's a difference of population measurements. Here's what's unique. I saw some light coming out, and from that light, I have no idea which atom is in up and which atom is in down. That's what makes it fundamentally different from how people normally do these kinds of measurements, okay? And what that does is it leaves the atoms in a superposition state. So if they start in a superposition of up and down, after the measurement, they will remain in a superposition of up and down. We do not collapse the wave function via this measurement. Here's an example. If you didn't know anything about this, the short story of it is, I'm just going to measure the quantum fluctuations and subtract them out. I'm just going to treat it like the quantum noise is just a source of noise. Let's just measure it and subtract it out. Let's build a feedback loop around it. Get rid of it, okay? And so here's an example. We start with all the atoms in the lower spin state. We apply a pi/2 pulse to put the atoms in a superposition of spin up and spin down. And then we measure the spin projection, JZ, via these cavity frequency shifts. We label the measurement outcome JZ sub F for final measurement of the spin projection. And on each trial, we get a definite outcome. And so we repeat this many times, and we get a definite outcome, say all these blue points with the scatter. But we can repeat the experiment where we also put an additional little rotation of the polar angle, just a few milliradians, okay? And those will be the red points over here. And you can see you can barely tell them apart. And the reason for it is the quantum fuzziness in the vertical direction for these two states. That's almost pure quantum noise you're seeing. We worked very hard to make that the case. So how do we subtract it out? The quantum noise, well, we just make a pre-measurement of it. So we create this superposition state. We measure the spin projection JZ pre, and then we apply this additional rotation or not, and then we measure the final spin projection JZ. And we take the differential quantity. If we plot the differential quantity, what you see is we've partially subtracted off and reduced the quantum noise while we've maintained our signal. We have more angular resolution as a result of this process. We have essentially collapsed with this first measurement into a squeeze state with reduced uncertainty along Z. And therefore, it's a sharper probe. Okay. How does this really work? If you're familiar with the idea, the basic idea, often we teach quantum measurement and we don't do it very well. It's a little bit sloppy. How does it really work? Well, in some sense, you start with a wave function whose distribution of possible spin projections JZ is some Gaussian distribution along the vertical direction here. You make a measurement of the spin projection JZ, and you get a measurement outcome that has this value over here. It's a definite outcome from your measurement. But there's some fundamental quantum uncertainty due to vacuum noise associated with the probe photons you're using to measure that cavity frequency shift. And so there's some uncertainty in your measurement outcome over here. And so as a result, what you have to do is kind of a weighted average between the prior, which is the initial wave function, and the new update which is the new measurement, and you basically get a weighted average. That is the pure state wave function, and it now has this distribution of JZs, which is narrower over here. And so it's just, you're using that first measurement and doing a Bayesian update to the wave function, and now you have this, this sort of more precise sort of pointer that you can use in experiments.
But in each measurement, you make a projection, right? It's a projected measurement.
Mm-hmm.
In what sense you're not collapsing into the
Because I don't know which atom isn't up. So I have a collective projection operator that's symmetrized over all the atoms.
I see, you just know the total JZ.
Yep, that's the magic.
So you just bias the distribution.
Via the measurement outcome.
Kind of a Bayesian.
And that's exactly it. That's exactly why we're calling it the Bayesian update. That's right. Mm-hmm.
So if you were to increase the wave time, then this would disperse further along the equatorial.
Correct.
and continue to narrow.
Correct. And then realities of the real experimental system kick in, and other bad things happen eventually.
Okay, so that's where you optimize the
Yep.
wave time.
The wait time is, it's really like the integrated average number of probe photons that you use to estimate the cavity frequency shift. It's sort of that pulse area that actually matters. Mm-hmm. Yep.
How does the time enter into this? Like how often you measure?
It's a continuous measurement, and it's really not so critical the time. It's like I'm going to use a coherent state of light that's in a pulse. I'm going to send it at my cavity, and I'm going to measure its properties when it returns. It's sort of what is the expectation value of the number of photons in that coherent state that you're using to probe.
You continuously measure.
Yeah, that's right. We actually do this on a homodine detector and measure quadrature sort of fields. We measure reflection. It's super complicated. I'm sweeping a lot of stuff under the rug here. Okay. I just want to highlight that if we scale the AB number, the standard quantum limit, you have an enhancement in your phase sensitivity. It looks like this. With this squeezing, we actually run parallel to the fundamental limit called the Heisenberg limit that you can't get past. And so this scales very well as you go to large AB number, which is what you would really like. Okay, let me just quickly highlight that we have taken these techniques that we've sort of spent a lot of years developing down the hall in my lab, and recently successfully applied them to measuring the frequency difference between atoms in one ensemble of a standing wave optical glass and another ensemble. We sort of shuttle atoms in and out. This is done in Jun Yi's lab in one of his systems, and I'm sort of a non-paid consultant. And so the atoms go up and down here, and we can sort of use this to create two squeezed sort of clumps of atoms, and we can make differential measurements between them. If you're interested, you can look here. Okay. There's another type of measurement that we do with atoms called light pulse matter wave interferometers. And the basic idea is the idea that if you have some atoms coming in, you can actually get them to absorb photons, and photons carry momentum, and therefore the atoms will recoil. And if something recoils, it means it moves. And so you can use that recoil to cause the atom to deflect and go along this path. But what if I put the atom in a superposition of having absorbed and not absorbed a photon? Then it both recoils and doesn't recoil. And we can actually make it go along multiple paths at once. We can reverse this with another pulse of light, and then we can actually interfere these two paths using a final pulse of light. That's called a matter wave interferometer. It is an optical interferometer, but replace light with a de Broglie wave. That's all it is. Okay? Lots of applications for fundamental physics as well as technology over here. One of the questions we had is we've developed these techniques for creating entanglement. Can we actually use squeezing or generate squeezing and inject it into a matter wave interferometer and see an enhancement? So that was one of the questions we had. So we did this in a rubidium system that was vertically oriented, and the atoms are sort of confined to move along fall along the vertical axis here. And we're going to inject laser beams along the cavity axis. They're going to give us all of our momentum kicks to put the atoms and manipulate and run this matter wave interferometer. So we can form what would be called a Mach-Zehnder interferometer with these pulses of light, and we describe the system on some block sphere over here, where the north pole is sort of one hyperfine state and one momentum state, another momentum state, and say spin down hyperfine state. We can see interference fringes as we scan the phase of this final, we play with the phases of the final lasers, and we can sort of see that there's coherence between these two paths and see an interference fringe. We can see that the phase of this fringe actually scales quadratically with time, just like if you drop a rock, 1/2 GT squared is the distance it falls. Same thing, except we're measuring units of lambda over here for this phase. And that's why it looks like this. It's inertial sensing of free fall. So we can actually use the Q and D measurements I talked about before to actually create a squeeze state, and we're going to use that to inject into an interferometer. However, I briefly want to tell you about another way to create squeezing, and that is, imagine that I have my resonance frequency in my cavity here, but now we've said that the cavity resonance frequency depends on the spin projection Jz. Let's just apply a continuous pump at a fixed frequency that's off resonance from the cavity mode. Well, if Jz changes, what it's going to do is it's going to change the amount of pump light that gets into the cavity. And so if I look at, that says that the number of photons inside the cavity depends on Jz over here. If I go back to that Q and D Hamiltonian, we'll just replace C dagger C with Jz, and lo and behold, you get something called a one-axis twisting Hamiltonian out of that. And so this allows you to actually generate unitary dynamics that can take an unsqueezed state and actually shear it. If the Bloch vector is above the equator, it wants to rotate this way. If it's below the equator, it wants to rotate this way. And this leads to a shearing of the quantum noise distribution, and you get squeezing. So I'm not going to show you data, but I'm going to say that this works. We can use both Q and D and one-axis twisting to create these entangled states. We do it in a little mini interferometer, and then we inject it into the real interferometer and see that we have more phase resolution at the output. And that's the first time that had been done in this system, this kind of light pulse matter wave interferometer. OK. In the short amount of time I have left, I would like to tell you about how we also explored realizing cavity-mediated interactions between momentum states. So there are no hyperfine labels involved anymore, no spin labels. They're in the same internal state. But we put atoms, for instance, one is at some average momentum P naught along the cavity axis plus h bar k, which is one photon recoil momentum. H bar k is the recoil of one photon. Or P naught minus h bar k. So imagine one atom is here and one atom is here in this momentum state. And we send dressing lasers in, and there's an intermediate optical excited state over here, but we're really, really far off resonance. So we're not going to resonantly excite it. So this atom could absorb that pump photon and actually emit a photon into the cavity. And before that photon has a chance to escape, the red atom can reabsorb it and go to the other state. They have flipped their momentum states. If I think of this as a spin half, hey, spin halves again. Everything's a spin half. Then we can rewrite this sort of process between atom I and atom J in terms of Pauli raising and lowering operators, and it looks like an all-to-all collective exchange interaction, except what's being exchanged now is momentum states in the system. Okay? So this was actually put forward in a theory proposal paper out of Murray Holland's group, and then we realized this in 2024. There are lots of things I could show you, but let me show you this interesting data right here. So if I put atoms in a superposition of spin up and spin down, of one momentum staying the other, those wave packets recoil from each other. They move apart in time. That's the simulation over here. And what that means is if I measure the sort of contrast of my interferometer as a function of delay time, as they separate, they can't interfere anymore. And so that's the black points. But if we turn on the interactions by putting on this dressing laser that induces momentum exchange, then what happens is we see the coherence last for a lot longer than it ought to. And the only way that can happen is if these wave packets are not actually moving apart from each other anymore. They're really staying overlapped with each other. Somehow, this total J squared term that's embedded inside of this total J plus J minus term is sort of binding these wave packets together. Okay? So here's a simulation of it when you don't have interactions and when you have interactions on. And that's exactly what this total J squared that's buried inside of this J plus J minus does for you. Okay? We can actually see that in the data where we actually measure that these wave packets are effectively bound by a spring by allowing them to begin to separate, and then we turn on the interactions and we see oscillations in the coherence as they bounce back and forth with respect to each other. And that's the oscillations you see right here. Okay. Oh man, it's 4:50. I'm going to stop soon, I promise. Let me tell you what this means, okay, by doing a Gedanken version of what I'm showing you. Imagine I have a collection of N atoms. They're sitting there. And I have a single photon gun. Pow. I shoot it. And I send this single photon collection of N atoms. Well, conservation of momentum says that at some later time, one atom is going to come shooting out of this cloud at h bar k over m. Okay? That's just normal. I'm telling you with the momentum exchange interactions, the system behaves like this. I send that photon in, it gets absorbed, but the whole cloud recoils. It's a collective recoil mechanism now, okay? The momentum of that one photon is absorbed by the whole cloud. And so it's really interesting because it's really similar to something called Mossbauer or Lambdicki spectroscopy, which has been incredibly enabling in our ability to make precision measurements, okay? So the first measurement of, for instance, the redshift due to GR was enabled by, for instance, Mossbauer spectroscopy. Today's atomic clocks, optical atomic clocks, rely on the Lambdicki trapping. And this is just qualitatively a whole new way of doing it, okay? So we find it very interesting. With that, I'm going to skip ahead. And I'd like to just tell you a quick summary that I've told you some of these things about sort of clocks over here and matterwave interferometers and creating entanglement. This idea of somehow suppressing Doppler dephasing or keeping coherence in the system. But we've actually been expanding the palette of kinds of interactions we can realize in these systems. For instance, now we can generate arbitrary all-to-all XYZ Hamiltonians. And we can tune those parameters as we want. And in particular, we realized this two-axis counter-twisting squeezing Hamiltonian, which was proposed 30 years ago, but no one knew how to do it. And it seems like we know how to do it now. In addition, we've extended some of these concepts. All the interactions in cavity QED have always been two-body in nature. It's all-to-all, but atoms only interact pairwise with each other. We now have demonstrated in the experiment that we can realize 3- and 4-body interactions as well. And then finally, we are looking at harnessing dissipation in our system as a resource to see if we can sort of realize interesting states for metrology and quantum sensing. I am not going to talk about this. This is story number 3, okay? But if I was going to tell you about how we can take some of these interactions in controllable disorder in order to emulate dynamical phases of BCS superconductors. And I think this is going to be very exciting going forward. I am going to do the most important part of this talk now. The most important part of this talk is this. There was a day I could go down to the lab and I knew what all the knobs were. I could turn anything and I was competent. There was a pretty good chance I was going to improve the experiment. Unfortunately, those days have gone by. And the reality is, at some point you realize, holy cow, maybe you don't have to do that because you have amazing students and postdocs. And it's such a pleasure to have amazing students and postdocs. And I just really want to thank them for all the hard work they do. They really are the people who make this work, not me. Okay, they spend the hours and the time to make this go. I'm so appreciative of that. I'm also appreciative of all of our collaborators, both on the theory side as well as the experimental side. So with that, I'm happy to take questions. Sure. Okay, here's how I think I'm going to answer that. Really what sort of disrupts this is if you have inhomogeneity in the transition frequency of the absorbers. And the trick is, so long as the interaction scale is energy scale is much larger than that spread in the transition frequencies, then essentially this works great. And it's only when the inhomogeneity becomes comparable to the energy scale of the interactions that you begin to get sort of partial sort of recoil. And that's what leads to the partial sort of, when I show you the data where the coherence didn't stay at 1, it sort of came down and plateaued. It's because we're in a regime which was kind of in a crossover regime where the inhomogeneity was comparable to the interaction strength. And so it sort of settled at some intermediate value.
So like 50% of the photons basically move the entire planet? Something like that, the border?
I think it's fair to say that if your long-time contrast is 50%, then 50% of the time you would probably see a photon come screaming out in that Gedanken experiment. Mm-hmm.
Thanks, Jim. I have a question about how strong the coupling between your atoms and your cavities. You need to be strong
Yeah. So in our case, we are focusing on collective physics rather than, for instance, trying to drive like single qubit-like interactions between just two atoms inside the cavity. And in that limit, what's actually important is something called the collective cooperativity parameter, which is n, the number of atoms, times c. C, if you don't know what C is, cooperativity, it just says, imagine you put a single atom in its optically excited state inside of your cavity. You tune the cavity onto resonance with the atomic transition. C is kind of the factor that tells you what's the probability that I decay into the cavity. That's kind of what C is. And our C is about 0.5 in a lot of our experiments. So about half the time, a single atom wouldn't even notice the cavity is there. That's not a very strong coupling. On the other hand, we can work with 1 million atoms, and you get a sort of quantum interference effect that allows those in atoms to sort of have superpositions of dipole moments that give you interference terms that enhance the rate at which you would emit into the cavity mode. And so that is the number that matters, and that's sort of order of 1 million in some of our experiments, 1,000 in other experiments, depending on our atom number. Mm-hmm.
So this new type of laser,
Yeah.
how do you refer to it?
Well, we refer to it as a super radiant laser after Dickey, who, if you don't know Dickey, you should read up on him. He was an amazing physicist. But he had this idea that you could put atoms in free space, and due to the symmetry of the atomic wave function, you could get a stimulated emission effect.
That's not my question, but I just
Yeah, but that's where the nomenclature is coming from.
Can you understand it as just the James Hamiltonian?
Oh, totally. Yep, totally. It is the James Hamiltonian, the limit, where you adiabatically eliminate the cavity mode because kappa, the cavity damping, is so large. So you put the atoms on resonance with the cavity mode, and then you just say, I'm going to adiabatically eliminate the cavity mode using the fact that kappa, the cavity decay, is very, very large, much faster than any of the other dynamical timescales. That's how you would get to it on the math side. Mm-hmm.
One last question.
In the generation of the multi-body squeezing
Yeah.
the Bayesian inference, would you win at all if you probe the cavity with like a squeeze state of light as opposed to a Koenig state?
Yes. So in the end, what we're really doing when we measure the cavity frequency shift is we send a coherent state of light at one of the two mirrors. It's a single-ended cavity in the sense that if light goes in, it almost all comes out a single, the input port, okay? So you would send the light at that. We look at that reflected light, and we detect it on something called a homodyne detector. And we measure what you might think of as the phase quadrature. In reality, it's just like the quadrature orthogonal to the average orientation of the phasor describing the light. And so if you sent in phase squeezed light, then in principle you get more precision. I think it's an interesting thing to do, okay? The thing with squeezed light you have to be a little bit careful about is it's fragile. It's really easy to lose photons, especially in a free space system coupling to atoms. It doesn't mean it's not doable. So I think there's room to win. There's even room to win where we've been thinking about on the theory side recently, that if you wanted to drive this one-axis twisting, it turns out what you want to send at the cavity is probably amplitude squeezed light. So depending on whether you're doing this Q and D probing, there you use phase squeezed. If you want to drive these unitary dynamics with an off-resonant probe, then you actually rotate your squeezing axis, and now you do amplitude squeezing, and that's where you win. Great question.
How are the questions? And thanks.
Thank you.